Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Materials Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or tutoring, then check out the links in the description below. Now let's just get started on our set of questions for today's session. Okay, so question 1 says to draw the Lewis structures of N2H4, N2H2, and just regular diatomic nitrogen. Okay, so let's start off writing the first Lewis structure that contains 2 nitrogens and 4 hydrogens. So before we write Lewis structures, we want to first calculate the total number of valence electrons. In the case of nitrogen, there are 5 valence electrons, and we have 2 nitrogens, so we multiply this by 2. And in the case of hydrogen, hydrogen has 1 valence electron, and we have 4 hydrogen atoms. So if we add these values up, we get a total of 14 valence electrons. So now let's try to write out the Lewis structure over here on the right. We'll have our 2 central atoms be the nitrogen, and then I'll just draw single bonds to each of the hydrogens. Okay, so at this point, I like to count out how many electrons I've drawn so far. So each bond contains 2 bonding electrons, and we have a total of 5 bonds, so we have 10 electrons drawn so far, so I just need 4 more. So I'm just going to put a lone pair on each of my nitrogens. Okay, so that's the Lewis structure for part A. Part B is N2H2, so there's 2 less hydrogens this time. And now let's calculate the total valence electrons for this molecule. Nitrogen is 5 electrons times 2, and this time hydrogens is 1 electron times 2. Okay, so then we get a total of 12 electrons for this structure. And again, we're going to start off writing our 2 hydrogens, and then a single bond to each of the hydrogens. So notice that our nitrogens don't have a full octet yet, so I'm just going to draw an extra bond before writing down my lone pairs. Okay, so now let's count out how many I've drawn. So this structure has 12 electrons, everything has a full octet. So this is the correct Lewis structure for our second molecule. And now let's just do it for diatomic nitrogen. The number of valence electrons will just be 5 times 2, which is 10. So let's write our 2 nitrogens single bonded together. And typically with diatomic elements, nitrogen would have this triple bond in between the 2, and then each would carry a lone pair. So let's double check and count out how many electrons are in this structure. We have 2 for each bond, so 6 plus 4. So this is 10 electrons, so this is the correct Lewis structure for diatomic nitrogen. So now let's see what the junior tutor said. For the first structure, step 1 is to list the elements, their valence electrons, and determine the total valence electrons. If a charge is present, add the value of the charge to the total valence electrons when it is a negative charge, and subtract if it's a positive charge. So we didn't need to do that for any of our molecules since they were all neutral. So for the first structure, they got 14. And then they drew it out step by step. So first is the skeletal structure. And then next they added the 2 lone pairs, and that was their final structure. For part B, they did the same thing. They got 12 valence electrons. They made a double bond between the nitrogens. And then lastly, they gave each nitrogen a lone pair. Then for the diatomic nitrogen, they have 10 valence electrons and drew a triple bond. And then finally added the remaining 4 electrons as lone pairs on the nitrogen. Okay, so this solution is correct. Okay, so question number 2 is, what is the Lewis structure of tetrachloroiodide? Okay, so first let's find the total number of valence electrons for this ion. So in the case of iodine, iodine has 7 valence electrons, and chlorine has 7 valence electrons as well. And we also have 4 chlorine ions, so we multiply this by 4. And then since this ion has a negative charge, an overall -1 charge, we're going to add an additional electron to our total valent electron count. So if we add these all up, we get a total of 36 valence electrons. So now let's draw our iodine as our central atom. And then I'm just going to draw single bonds to all of my chlorine atoms. And then from here, I'm just going to add all of the lone pairs on my chlorines. Okay, so now I just like to count out to see how many electrons I have so far. So each bond contains 2 bonding electrons, and each chlorine has 6 non-bonding electrons. So I only have a total of 32 electrons, so I just need to write down 4 more in order to get my total number of 36. So for the last 4, I'm just going to add them as lone pairs on my iodine. So now I have total of 36 electrons, and now I'm just going to calculate the formal charge of each of the ions. So I'll write the equation for formal charge up here. So formal charge is equal to the number of valence electrons minus the number of non-bonding electrons. So these are all the electrons that are in the form of the lone pairs. And then minus the number of bonding electrons divided by 2. Okay, so let's calculate the formal charge of one of the chlorine atoms first. So all of the chlorines are the same, so I only need to do this once. And the number of valence electrons for chlorine is 7. And then each of the chlorine atoms have 6 non-bonding electrons. And lastly, chlorine has a single bond, so each bond contains 2 bonding electrons, and then I just divide this by 2. So 7 minus 6 minus 1 is 0. So each of my chlorines are neutral. And then if I were to calculate the formal charge of my iodine, iodine has 7 valence electrons, and the number of non-bonding electrons is 4. And there are also 4 bonds to the iodine. So we have a total of 8 bonding electrons, and then we're just going to divide this by 2. So 7 minus 4 is -1. So now I know that my iodine is the atom that carries this negative charge. So now let's see what the junior tutor said. Tetrachloroiodide ion has a molar mass of 268.7 grams per mole. And to draw the Lewis structure for this compound, the first thing we need to do is to determine the total number of valence electrons. So they got 36. So therefore, the tetrachloroiodide ion has a total of 36 valence electrons. Since iodine is the less electronegative element compared to chlorine, we put it as the central atom. By obeying the rule of the octet and by distributing the total number of valence electrons around the corresponding element, we will have the following Lewis structure of the compound tetrachloroiodide. Okay, so they got the same thing. And to check, we can count for the total number of valence electrons using the dots and bonds from the illustration above, and we will still have a value of 36. Okay, so this solution is correct. And then I'm just going to specify that iodine carries the formal charge of -1. Or iodine has the formal charge of -1. And chlorine atoms have a formal charge of 0. Just so that we can know where the -1 charge came from. Okay, so question 3 is like a multi-step question. So first, we need to draw the Lewis structure for silicon tetrachloride, in which the central atom obeys the octet rule, and answer the following questions based on your drawing. What's the number of unshared pairs on the central atom? The central atom forms this many bonds and this many double bonds. So we just need to fill in the blanks. So first, let's write the Lewis structure. We need to find the total number of valence electrons for this molecule. So for silica, there's 4 valence electrons. And in the case of chlorine, a chlorine atom has 7 valence electrons. And there are 4 atoms of chlorine. So we get a total of 32 valence electrons. Okay, so now I'm just going to draw my silica as my central atom. And then I'm just going to draw 4 single bond to chlorine. And I'm going to add all of the lone pairs on chlorine as well. Okay, so if I count out how many electrons I've drawn so far, I already have my 32 electrons. So now I can try to answer the questions. The number of unshared pairs or lone pairs on the central atom is. So if we count it out, there are no lone pairs on the central atom. I'm just going to say 0 lone pairs. The central atom forms how many double bonds or single bonds? So there are 4 single bonds. And then lastly, how many double bonds does it form? And there are no double bonds in the molecule, so just 0. Okay, so now let's see what the junior tutor said. Step 1 is to list the elements, their valence electrons, and determine the total valence electrons. If a charge is present, add the value of the charge to the total valence electrons when it's negative, subtract if it's positive. So they got 32. Step 2 is to draw the skeletal structure. Note one bond contains 2 electrons. Step 3 is to distribute the remaining valence electrons. And lastly, they got 0 lone pairs, 4 single bonds, and 0 double bonds. Okay, so this solution is correct. Okay, so question number 4 is draw a Lewis structure for formate ion. So the formate ion is HCO2 minus. So now let's find out the total number of valence electrons for this ion. Hydrogen has 1 valence electron, carbon has 4, and oxygen has 6. And there are 2 oxygen atoms, so we multiply this by 2. And then lastly, since the entire ion carries a -1 charge, I'm going to add an additional electron to our final count. And then if we add these all up, we get a total of 18 valence electrons. Okay, so now let's try to write the Lewis structure for the formate ion. I'll start off with the carbon. So the carbon will most likely be single bonded with the hydrogen. And then I'm just going to draw single bonds to each of my oxygens. So notice that carbon doesn't have a full octet. So now I'm just going to make one of these oxygens have a double bond and draw all of the lone pairs in. And then from there, I'm just going to count out how many electrons I've drawn so far. So each bond contains 2 bonding electrons, and we have 4 bonds, so that's 8. And 18 electrons are drawn if we add them all up. So now I just want to calculate the formal charge of the ions. So the equation for formal charge is the number of valence electrons minus the number of non-bonding electrons minus the number of bonding electrons divided by 2. Okay, so let's see what the formal charge of hydrogen is. So hydrogen has 1 valence electrons. There are no lone pairs on hydrogen either, so there are 0 non-bonding electrons. And finally, there's a single bond to the hydrogen, so we have 2 bonding electrons divided by 2. So hydrogen has a 0 formal charge. So let's do the same thing for our carbon. Carbon contains 4 electrons. There are no lone pairs, so there's 0 non-bonding electrons. And the number of bonds to carbon is 4, so we have 8 bonding electrons divided by 2, which is also 0 in the end. And now let's do the formal charge of our oxygen that has the double bond. Oxygen has 6 valence electrons. For the double bonded oxygen, there are 4 non-bonding electrons. And then lastly, there are 2 bonds from the oxygen. So we have 4 bonding electrons divided by 2. So 6 minus 4 minus 2 is just 0. And now let's do the formal charge of our single bonded oxygen. So this still has 6 valence electrons. The number of non-bonding electrons is 6. And there's only a single bond to this oxygen, so there's 2 bonding electrons divided by 2. So in the case of the single bonded oxygen, it has a formal charge of -1. So now I know that for the formate ion, the negative charge comes from the single bonded oxygen. So now let's see what the junior tutor said. Follow the following steps to draw a Lewis structure. Step 1, calculate the total number of valence electrons, so they got 18. Step 2 is to connect all the atoms in the molecule with single covalent bonds to draw a skeletal structure. Okay, so then they said that carbon is selected as the central atom because it can form more bonds than oxygen and hydrogen. You would also say that carbon can be the central atom because it can form more bonds, but also because it is less electronegative than the oxygen. So typically the least electronegative element would be the central atom, with the exception of hydrogen, since hydrogen can only form 1 bond. So that's why carbon is most likely going to be the central atom. So oxygen, which needs just 2 electrons to reach neon's noble gas configuration, forms 2 bonds maximum. And hydrogen, which just needs 1 to reach the noble gas configuration of helium, forms only 1 bond. Therefore, carbon is placed at the center. Oxygen atoms and hydrogen are made to bond with carbon, and there are 3 bonds in the skeletal structure. Okay, so then they place the remaining 12 electrons on the atoms so that the octet of the max atoms gets filled. And then now they added a lone pair on the carbon since it didn't have a full octet. And then they calculated the formal charge of all of the atoms in the molecule. Make sure that they have the smallest possible formal charges. Okay, and they got -1 for the singly bonded oxygen and got the correct Lewis structure. So this solution is correct. Okay, so question number 5. What is the best Lewis structure for, I believe this is called the bromate ion, but basically BrO4 minus. And what is the formal charge of the bromine in the structure? So first, let's count out the total number of valence electrons. Bromine contains 7 valence electrons, and oxygen contains 6, and there are 4 oxygen atoms, so we multiply this by 4. And finally, since the overall ion has a -1 charge, we're going to add an additional electron to our count. And this gives us a total of 32 valence electrons. Yeah. So now let's draw bromine as our central atom. And then I'm just going to form single bonds to each of my oxygen atoms. So notice that none of the oxygens have a full octet yet. Let's see what happens if I drew in all of the lone pairs on oxygen. Okay, so right now, everything looks like it has a full octet, but if we were to calculate the formal charge of each of these atoms, then you'll notice that each of the single bonded oxygens will have a -1 charge. So we're going to form double bonds for 3 of them only. And bromine is one of those elements that can have more than 8 electrons in its valence shell. And we're left with the following structure. So now let's also double check to see how many electrons are in this structure. So if we count them all out, each bond contains 2 bonding electrons. And we have 1, 2, 3, 4, 5, 6, 7 bonds. That's 14. And we have 32 electrons in total. So from here, let's calculate the formal charge of each of the ions, or each of the atoms. So the equation for formal charge is the number of valence electrons minus the number of non-bonding electrons minus the number of bonding electrons divided by 2. Okay, so first we're going to calculate the formal charge of bromine. So this was asked in the question, so let's just find out what its formal charge is. So bromine has 7 valence electrons, and this bromine contains 0 lone pairs, so there are no non-bonding electrons. And lastly, there are the 7 bonds to the bromine, so we have 14 valence electrons. And if we divide that by 2, we get 7 minus 7, which is just 0. So the bromine is neutral. And now let's do the formal charge of the 3 double bonded oxygens. So the double bonded oxygens, they'll have 6 valence electrons. Each of them have 4 non-bonding electrons. And they all have the double bond. So there are 4 bonding electrons in total, divided by 2. So all of the double bonded oxygens would be neutral. And finally, let's calculate the formal charge of the single bonded oxygen. There are 6 valence electrons. The number of non-bonding electrons for the single bonded oxygen is 6. And lastly, since there's just a single bond, there are 2 bonding electrons that we divide by 2. So 6 minus 1 is -1. So we know that the single bonded oxygen contains the -1 formal charge. So now let's see what the junior tutor said. They have the same structure, and they have the equation for formal charge, number of valence, minus, so they count the number of bonds attached to it. So that's another method of calculating the formal charge. Instead of doing bonding electrons divided by 2, you can simply just count the number of bonds. So it's the same thing, minus the number of non-bonding electrons. And they got a formal charge of 0 for the bromine, and this solution is correct. Okay, so question number 6 is to give the name for SNO. Is it tin 1 oxide, tin 2 oxide, tin 3 oxide, or tin 4 oxide? Okay, so first let's analyze the type of compound we have. So you'll notice that we have tin, which is a metal, and we also have oxygen, which is a non-metal. So these are bonded together through an ionic bond, so therefore we have an ionic compound. So it's always important to know the type of compound you have because each of them have different rules. So now I'll just write the rules of naming ionic compounds. So when we name ionic compounds, we first want to name our cation. So cations are the positively charged ions. So this, for the case of our example, this is your metal. So you would just either say the metal's name, or if it was a positively charged, like polyatomic ions such as ammonium, then you would just name the cation. And then secondly, you name the anion, which, as you can guess, is the nonmetal. And you add the suffix of "ide" at the end. In the case of polyatomic anions, you would just simply name the polyatomic ion. I'm just going to write that down. This doesn't pertain to our example, but it's still important to know. So you don't need to add the "ide" at the end. And then for step 3, Depending on the type of metal you have, it can have different oxidation states. So if your metal has more than one oxidation state, we can specify which one that is. And we do that by using the Roman numerals and the brackets. Or you can use like the Greek prefix, but I tend to prefer just using the Roman numerals. Might be easier. Okay, so now that we know all of the rules to naming ionic compounds, we just need to figure out the name of the example that was given. So basically, for all the options that they gave us in the question, they already pretty much wrote out the cation and the anion that ends in "ide", and basically we just need to figure out what oxidation state tin is in. So to do that, we first need to look at the overall charge of our ionic compound, and you'll notice that it's just neutral. So whatever the oxidation state of our oxygen is, we know that the tin must have the same magnitude of oxidation state but the opposite charge. So for example, oxygen usually has an oxidation state of -2, with the exception if it was in a peroxide, but in this case it's not. So oxygen has an oxidation number of -2. So since we have a neutral compound, then we know that the tin must balance out this -2 charge. So it's going to have an oxidation number of +2. So therefore, we can just say that the name is tin 2 oxide. Okay, so now let's see what the junior tutor said. Given compound is an ionic compound, hence name it by naming the elements present. However, tin is a transition metal having multiple oxidation numbers, so it's necessary to determine its oxidation number in the compound. Remember that the oxidation number of oxygen is -2, hence in order for the compound to be neutral, the oxidation number of tin should be +2. Ergo, the name of the compound is tin 2 oxide. Okay, so this solution is correct. Okay, so question 7 is just to draw all the products of these following reactions, including all the stereoisomers. So these are just different examples of how one can add bromine to like an alkane. And I'm just going to show what the junior tutor said, since you can get very like in depth about it. So free radical halogenation of alkanes with bromine and light or heat produces bromoalkanes. Free radical halogenation is regioselective and replaces the hydrogen atoms with the halogen in the order of allylic or 3 degree, 2 degree, or 1 degree carbons, and then methyl. This order of reactivity can be predicted on the basis of radical intermediate stabilities, which follow the same order. So depending on the type, I'm just going to write this down. So this is question number 7. So the most stable radicals are your allylic. So this is when it contains a double bond. So for example, if there's a double bond on the carbon beside it, and your radical can just be shown right there. So this is less reactive than if you were to have a tertiary. I'll just do it in the same format, like a 3-degree radical. Like this as an example. So 3-degree radicals are more stable than your 2-degree, which can just be in the middle here. 1-degree will be at the end. And then for methyl, this is just if you have your 3 hydrogens and a radical on that carbon. So this order of reactivity can be predicted on the basis of radical intermediate stabilities which follow the same order. Radical intermediates are analogous to carbocations in the sense that they are stabilized by the same interactions, namely resonance delocalization and hyperconjugation with attached alkyl groups. When radical halogenation produces a chiral center or takes place at a hydrogen on an existing chiral center, the product is an equal mixture of R and S and enantiomers. Allylic bromination occurs at high temperatures. Heat is the radical initiator using the halogens themselves. Bromination using N-bromosuccinimide or NBS is initiated by light, and the mechanism involves a radical chain process with a resonance delocalized allyl radical intermediate. So I'll kind of show what a brief mechanism would look like for when you do allylic, or let's just look at the first example. You can show the movement of one electron just by using single arrows like this. And that's how a bromine can be formed. And you're also left with a bromine with another radical. So radicals are when you just have that single electron on your atom. So now if we look at what the junior tutor said with all of the different examples. So for part A, you can see that they included all the different types of products you could possibly get if you reacted the bromine with heat and light. and they just showed both the R and the S configurations. They did the same for butane. Bromine can be at the end, in the middle, with the different configurations. And for NBS, which is the N-bromosuccinimide, they can either be beside the double bond on one side or at the end here. These are all the different products you could get for D. This is E. And finally, F. Okay, so everything looks good. So the solution is correct. Okay, so question number 8. What is the Lewis dot structure of caffeine? Show all the electron pair electrons. What is the hybridization of the indicated electrons? Okay, so they already drew out the main structure of caffeine, and basically we just need to add all of the lone pairs if applicable. Let me just draw out the molecule. Okay, so I just drew what was given in the question, and basically we just need to show all the lone pairs. So basically all of the nitrogens will have a single lone pair. Just to complete their octet. And finally, both of the double bonded oxygens will contain 2 lone pairs. Okay, so this is the Lewis dot structure of caffeine. And now we need to know the hybridization of each of the indicated atoms. So this is pointing at, I believe, the carbon right here. And we are looking at this nitrogen, which is B. And then finally, this carbon here, which is C. Okay, so one way I like to figure out the hybridization of an atom is just to find the number of charge clouds. So I'll explain what the term charge clouds means. Find number of charge clouds. So what I mean by charge cloud, this can either be a lone pair or it could be a bond pair. Or like a bonded atom. And after you count out how many charge clouds you have, this will help you when you find out your hybridization. So we have sp3 hybridization when we have 4 charge clouds. We have sp2 when there are 3. And we have sp when we only have 2? Okay, so now let's look at the atoms that they give us. So carbon is like right here. So if we count out its number of charge clouds, there are no lone pairs on this carbon, but it is bonded to 3 other atoms. So therefore, this is going to be sp2. Now let's look at B. This is our nitrogen. It has 1 lone pair and 2 bonded atoms. So that means it has 3 charge clouds as well, and it will also be sp2. And lastly, this carbon contains 3 bonded atoms to 2 nitrogens and a hydrogen. So C is also sp2. So an example of sp3 would be like this carbon right here. It's bonded to 3 hydrogens and a nitrogen, so that's 4 bonded atoms, or 4 charge clouds, so this would be sp3. And there's no example of any sp atoms, but an example, I'll just write one down here, would be if you had carbon that was triple bonded to another carbon. This central carbon has only 2 charge clouds, so this would just be sp. Okay, so that's a brief explanation on how one can calculate hybridization. Now let's see what the junior tutor said. They drew out the Lewis structure and said that all of the atoms had an sp2 hybridization, so this solution is correct. Okay, so question number 9. What is the definition of atomic orbital? Okay, so we have atomic orbital, so this can help describe where an electron is likely to be found in an atom. And the junior tutor said that an atomic orbital can also be a mathematical model that describes the probability of locating an electron in a certain region in space. Yep. And atomic orbitals are more commonly recognized as the shapes formed by the orbitals in the sp, d, and f subshells. So they have an example of all the different shapes that you could possibly get. Moreover, atomic orbitals can be described by 3 quantum numbers: principal quantum number, angular momentum quantum number, and magnetic quantum number. Additionally, each orbital can contain 2 electrons only. These electrons must have opposite spins, as described by the spin quantum number. So also, each electron has a specific set of quantum numbers, so you'll never find 2 electrons that have the same quantum number in an atom. So that's what kind of makes them unique. So this solution is correct. Then I'll just say what I wrote as well. Okay, so question number 10. The heavier group 15 elements can expand their octets. What is the Lewis structure for arsenic hexafluoride? And you need not include the charge on the ion, but if you wish, you can place it on the central atom. To change the atom, double click on the atomic symbol. I'm guessing we can't really do that, but please include all non-bonding electrons. So first, let's count out the total number of valence electrons for this ion. Arsenic contains 5 valence electrons, and fluorine contains 7. And there are 6 fluorine atoms, so we multiply that by 6. And we're going to add an additional 1 electron since the overall charge is -1. So if we add these all up, we get a total of 48 valence electrons. So now I'm just going to write arsenic as my central atom. And then I'm just going to symmetrically draw all of my fluorines all around. And I'll fill in the lone pairs on the fluorines as well. And then from here, we can count out how many electrons I've drawn so far. So each bond contains 2 bonding electrons, and each of the fluorines contain 6 non-bonding electrons. So if we count that all out, we get our 48 electrons already. So now we can double check and just calculate for the formal charge, which is equal to the number of valence electrons minus the number of non-bonding electrons minus the number of bonding electrons. So first, let's calculate the formal charge on one of the fluorines. So all of the fluorines are the same, so we just need to do this once. So fluorine has 7 valence electrons, and the number of non-bonding electrons are in the form of the lone pairs. So there are 6 non-bonding electrons, and there's only 1 single bond, so there are 2 bonding electrons divided by 2, making the fluorine having a 0 formal charge. And then let's do the same thing for the arsenic. Arsenic has 5 valence electrons, and there are no lone pairs, so we write 0 non-bonding. And then there are 6 bonds to the arsenic, so we have 12 bonding electrons divided by 2. So 5 minus 6 is -1. So this is why we need to draw the negative charge on our central atom. So now let's see what the junior tutor said. They have the same structure, and the arsenic has the negative charge. So this solution is correct. I think we have time for one more quick question. So question 11, what is the Lewis structure for selenium trioxide? Okay, so for the total number of valence electrons, selenium has 6, and oxygen also has 6, but we have 3 oxygen atoms, giving us a total of 24 valence electrons. So first, let's draw selenium as our central atom. And then I'm just going to draw single bonds to each of my oxygens. And if I were to draw in all of the lone pairs on my oxygens, It'll kind of look like this. So this gives us 24 valence electrons, except all of these oxygens would have a negative charge, and we want a neutral compound. And also our selenium doesn't have like a full octet. So we are just going to make double bonds from each of our oxygen atoms. So selenium is one of those examples where it can have more than a full octet. So this is why we are able to draw double bonds all around. And now we have a neutral molecule, and everything has a full octet. In the case of selenium, there's more. And let's see what the junior tutor said. They have their step-by-step guide. Make sure the atoms follow the octet. Strictly have 8 valence electrons. Minimize the formal charge if possible. And now they applied it to the question. Oxygen follows the octet rule strictly. Moreover, since it has 6 valence electrons already, it would typically create 2 bonds only to completely fill its valence shell. Oxygen is unlikely to be the central atom because it creates a few bonds only. Selenium, on the other hand, can exhibit expanded octet and create multiple bonds. So this is, given the explanation in step 1, the logical arrangement is having selenium in the center. And then they showed how all the double bonds can be formed. And they included the equation for formal charge. So if we were to calculate the formal charge of all the atoms, it would just be 0. So this solution is correct. Okay, so those are all the questions for this session. And if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. And if you'd like to submit a question of your own, then check out the links in the description. And also, if you enjoyed today's video, you can leave it a like and a comment, or share it with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.